Awesome. Hi, everyone. Can you hear me? I'm going to assume you can hear me. So, yeah, I'm Adi. I'm a PhD student at the University of Chicago with Ash Clerk. And this is some work that we've done in collaboration with Arvind Murugan at U Chicago. Some of you might know. And yeah, the title of my talk is Equilibrium Propagation and Non-Equilibrium Quantum Systems. There's been a lot of discussion at this conference about, thinking about doing these kind of EP style methods and whether these would work in dissipative systems or whether they wouldn't. And in general, the consensus seems to be when you have like a very nonlinear dissipative system, this is hard to do exactly. What I'll argue today is that actually in the context of quantum systems, we can actually find a class of systems that are like experimentally relevant, where you can actually extract such exact gradients and do this kind of training technique. So what I'll do is I'll quickly set up the problem that we have and go over how EP works in the context of our system. I know it's a bit of a repeat, but hopefully it'll be a little informative as we go through. And our work is essentially showing that we can do equilibrium propagation exactly, using exact gradients in sort of two experimentally relevant models. One is a dissipative transverse field Ising model, and one is sort of a bosonic lattice model with some quadratic driving. Great. So the general learning problem is, as an example, consider a simple 5-spin system. I can partition this into inputs and outputs. These all have control fields associated with them. This X here would be the input for my system. These thetas are going to be sort of the parameters that I'll train. And I can choose to read out certain observables on these spins, right? And there's a Hamiltonian that describes how all these things are coupled. And now I have like an input-output relation, which is the outputs are these observables, the inputs are the drives, and what I call my input spins, right? And the million-dollar question, of course, is can you actually do training to learn these thetas, to learn some sort of target data or some target function that you care about? And the question then is how do you actually you want to do gradient descent, so how do you actually calculate these gradients of some cost function, right? And the whole game is that we want to do some physical learning, so you want to extract these gradients from doing physical experiments. And the way you would do that is, you would sort of decompose this cost function into some error vector that contains all of your information about the cost function. This is sort of from work done by Clara and Florian. And what you want is these gradients. These are gradients of some physical observables in my system with respect to some parameters, which are my training parameters. And sort of the most naive way you would do that is this parameter shift type method, right? Like I will initialize my system with some initial drive theta j, perturb it, and get this gradient. And this would work, but like, of course, the big problem with this is it scales pretty badly in the number of the training drives that you have, because for each drive that I want to train, like theta 1, 2, 3, 4, I have to do sort of a separate perturbation. And so this scales very badly in the number of state preparations I have to do. And this is even worse when you think about the fact that what we're looking here at is closed systems. And so I really have to be sitting in some ground state or some equilibrium state. And that requires you to cool down to the state, which in the context of many-body systems is generally like a pretty hard thing to do. So EP kind of saves this problem partially, right? Like at least the scaling problem goes away, because the whole game here is that you have a free phase, you measure the observables that you care about in the present state of the system. I perturb everything by something proportional to this error vector, read it out again, and magically, well, it's not magically, but all the gradients that I care about happen parallelly. So I can update as many parameters as I want simultaneously, independent of system size. And this is sort of the big promise, right? And the two big upshots are, of course, the fact that it's a two-phase update. But another very useful thing here is that it's a local learning rule, which basically means that, like, to update drive theta j, I actually only need to measure an observable on that spin. And what that means is I actually don't need to know what's going on in the rest of the system. I can just do local things and update it. This is sort of like also very nice about EP. And so, why does this work? Well, this comes from this idea that, people have hinted at throughout the day, which is this idea of like reciprocity, or what we call sort of just having symmetrical derivatives in the system. It's like if you start from something like parameter shift, which is like this you can always do, and you sort of just think cleverly about how to use your symmetrical derivatives, you can sort of reach doing this EP. But what does this sort of boxed equation actually mean? Well, physically, it's a statement of equivalent linear response. So it's saying that if I kick drive theta j and measure observable OL, it's sort of the same as doing kicking drive theta L and measuring observable OJ. So this is nothing crazy, but this is just that is the statement. Like that is the only thing that you actually need. In a closed system, when you have equilibrium, you all can always write down a free energy. So like, if I'm in some ground state, I can always write down this F. And because this F is symmetric and the second derivatives commute, you always have this sort of reciprocity or just this symmetrical derivative. So this is just a statement of the fact that I have a free energy when the system is in equilibrium, right? And so the question you might ask is, of course, why do you use dissipative systems at all if this is sort of all working? And the big advantage of using a dissipative system, which is sort of described here by this like Lindblad master equation. If you're not familiar, the details are not too important. The point is that now I actually have some dissipation in my system, and the system settles to a non-equilibrium steady state. What's important here is this is not described as some free energy. This is truly a non-equilibrium quantum steady state, and the big upshot is now I can do all my measurements in this non-equilibrium state. And I know how to prepare it because the dynamics naturally prepared this steady state by just like waiting for long enough, right? So you don't have to worry about this like magic fridge preparation again and again in the context of a closed system. The big problem, of course, is that you don't have these symmetrical derivatives or this reciprocity in like generic dissipative systems. You just don't, because you don't have a free energy. And so our work sort of focuses on finding a class of systems which have like a more subtle notion of detail balance than you might naively think, and that actually allows you to recover some exact gradients for certain models. And essentially, detail balance is sort of tied intimately to notions of time reversal symmetry. And we identify a class of systems which have what we call hidden time reversal symmetry, which is sort of a notion of detail balance in open systems that gives you this sort of symmetry between the jump operators. It gives you a 2-time correlator symmetry between the jump operators. The details of HTRS is like a whole 20-minute talk in itself, so I'll try to just overview it very briefly, and then we can chat more about it if you want afterwards. But importantly, the systems that have this symmetry don't have this kind of, correlation symmetry for all the observables. It's only for a very small subset, which include these jump operators in the system, which are the lowering operators, right? And critically, the steady states here are like truly like quantum states with coherences. There's no, like, they're not just like simple thermal states. Like secretly, it's not like I'm forming a thermodynamic potential and using that, right? And these sort of correlator symmetries are very useful because by doing some linear response theory, you can this is actually a stronger condition than the gradients that you need. Where like, you can integrate out the dynamic part of it and then get these static reciprocity relations, which you need to do EP. So just very quickly about hidden time reversal symmetry. Like the formal statement is that like there exists some like anti-linear operator that conjugates your effective Hamiltonian and jump operators in this way. And if this exists for some system, then you have this symmetry. Now, you might say, what does this mean? And it's like, honestly, I don't know. This is just some mathematical thing that works. But the intuition that I like to think about is, if H is the system that I care about with some dissipators L1 and L2, physically, what is going on is the idea is that if I just imagine theoretically that there's a doubled system with like a negative Hamiltonian, and I have this like unidirectional waveguide that couples to it, which basically means that everything that dissipates out of this system goes into this system essentially. Then this whole cascaded system has a steady state that's pure, interestingly. And because that system is pure, there is some time reversal operator you can write down on this entire steady state. Just to be completely clear, like we're not proposing that you need to construct this whole thing. This is just a theoretical construction to understand what's going on. The symmetry is sort of true on just a single system that we care about. So the idea here is that like, this is just a way to understand what's going on. You can double the system with this specific formulation, and the steady state is pure. And when that's true, the system has this hidden time reversal symmetry. And this is not just some esoteric theoretical thing. There's a number of like very experimentally relevant models that have this symmetry. And a couple of my good friends in our group have spent their entire PhD sort of coming up with a bunch of these models that like have this symmetry and solved them exactly. And these are all very nonlinear systems. And today we'll talk about two of them, which is this transverse field Ising model and this bosonic lattice model. And we'll show how we can actually do EP in both of these using this symmetry. Great. So model one is 2 minutes. Oh, great. A dissipative. It's a transverse field Ising model, and the idea is all-to-all coupling, and I have some disordered drives where I encode all my information. I can encode my inputs here, training parameters. This has the following symmetry relation between the lowering operators, and like the important fact is the symmetry relation gives us a reciprocity that we want to do EP. And importantly, the observables in this reciprocity are not the ones that appear in the Hamiltonian. This is like sigma y. So this is kind of strange, but this emerges because the system has this HTRS basically, and this is sort of the key to do equilibrium propagation. And so the EP kind of proceeds in the same way that you would expect. It's identical to the closed case. I just measure the sigma y operators at theta, perturb them, measure it again. I get all these gradients exactly the same way you would do it in the closed system. There's zero difference, except now you're in steady states. This is nice. I'll quickly skip over the training. These are just some basic training results. And if you ask me a question about this, I will come back to it. But I will flash the second model that we have for just a second. This is also a really nice model. This is actually similar to the model that Daniela described in her talk, that we essentially have this like sort of bosonic lattice with some global Kerr coupling and this sort of squeezing quadratic drive with these MIJ like tunable couplings. And here the susceptibility symmetry that we find looks a little stranger, but where these observables Yij are essentially just imaginary parts of these correlators. But this is exact, and this is true, even though the model is completely dissipative. And then the idea is that, the control parameters become these MKLs, these sort of couplings. And so the way you would set up like a EP is like, I would maybe encode input into one of these couplings, X12, read out the imaginary parts of the, these correlators, these AI-AJ correlators for Y13, Y34, Y24. That gives me my output. And then EP proceeds exactly in the same way as you would in the closed setting. There's nothing else you have to do. And yeah, so that's kind of it. For me, the idea is just to emphasize that we extend EP to these like nonlinear driven dissipative models using this sort of subtle notion of detailed balance. And these reciprocity relations that we find are exact and they always hold for a model. And looking forward, the thing that we would want to maybe do is think about, if you're close to these models, like you don't need to be exactly these models, are the gradients approximately correct? Will this still allow you to learn? And another interesting direction is that the symmetry is actually dynamical, so we're not exploiting its full power when we reduce it to do these like static derivatives to do EP. So yeah, that's it from me. Thank you.
Questions? Thank you very much for the great talk. I was wondering about the spin model.
Yeah.
So different from the QEP we proposed, you actually read out and nudge with, you read out with sigma y, but you nudge with sigma
exactly.
x, right?
Yeah,
so
it's
could
a
you
little.
elaborate on this again?
Yeah, it's because the symmetry that we have is between sigma y observables and drives on sigma x. So everything is the same as you would do in your case, except like the observable that I would read out of each spin is sigma y, and that's because the symmetry has this form. Your outputs have to appear in the symmetry. They don't have to appear in a Hamiltonian, right? And so the idea would be here, like I would, encode all my drives in these x drives, theta, but the observable that I would choose to read out is just sigma y, and that comes from the fact that the reciprocity relation only exists for those sigma y type observables.
Thank you.
So what's wrong with this class of models? Why don't you just implement it?
Physically?
Yeah.
Well, I'm a theorist, so I don't know how to do anything. But no,
Yeah.
Well, I think one problem with the spin model is this is like all to all. I think that's generally a little difficult.
It has to be all.
It has to, yeah. So this model, with the dissipative model, this J has to be constant and all to all. And so this makes this one a little difficult to implement. But I think people have been. The other one, I think they have it. No, I don't know if I'm wrong, but I think this is. I was from talking to Briak. This seems to be the model that they've actually built. So as far as I understand.
So this
seems
available.
like it. Yeah.
So is there anything with implementing a real?
You would have to ask Daniela. Yeah.
Other questions? Wait, just a quick follow-up question also about the bosonic model.
Yes.
So here you have these phases into the I phi.
Yes.
So do you still have reciprocity when they're non-zero?
So you have to pick a gauge, basically. So here I pick all these are real. So you have freedom in either, like you have freedom in total n square parameters, not all. You can't just pick any things. You can pick any set of phases, and that sort of picks the operator that you care about here. Like if I set all the phases to 0, then it's the imaginary part of this. And if I set the phases to something, then it'll rotate sort of into a complex superposition of the, but like I can't train on these phases, basically. I have to pick a gauge and train on the couplings.
Right, and so what if you have non-zero loop fluxes, for example?
Yeah, so this is fine as long as like as in like if you just set all your if you have some like okay, so the phases, if there's like error in the phases, that'll cause an error in the gradients. But like as long as the gradients are these phases are fixed, then you can always find this exactly. They just have to be fixed. That's the caveat, I guess.
Is there a single steady state in the configuration that you consider?
Yeah, all of these models that have HRS have unique steady states, like provably. Yeah.
Thanks for the good throw. Intuitively in equilibrium propagation, we nudge the dual of the observables we're looking at. So we expect that we have good signal when we nudge a parameter, because we're nudging something that's the dual to what we're looking at. Here it seems to me that we're nudging something which is orthogonal to what we're looking at. Have you been able to see that you still get good signal?
Or like good size for these observables?
Yeah.
Yeah, so that's very interesting. So we've done the full simulations. This is pretty recent, this result, so I don't have like full, although we can, in principle, for any of these models, we have large scale numerics because we have exact solution for the steady state. We can analytically write it down. So we could check for this one. For the bosonic one, for the spin one, yes, but that observable sigma y is, the scale is set by the size of the dissipation, because when the dissipation is 0, the Hamiltonian is real, and so sigma y is just always 0 by complex conjugation symmetry. And so for like but when you have dissipation, then the size of that signal is set by the scale of the dissipation. So in theory, you can, as long as you can tune the dissipation, you can tune the size of the signal, essentially. But here, I'm not sure, but I think there'd be a similar argument. I think this would be set by the size of the signal would be set by the size of your dissipation.
Is the square on the sum, or is the sum of the square?
It's a square on the sum.
So also overall.
Yeah. It's actually, not that you care, but like this model is actually just like the spin model, but this now has like a SU11 type, between the X, Y, and there's like a Z I can write down, and that has like a SU11 algebra instead of a SU2 algebra that you would see in a spin model.
So there's a Lie algebra.
Yeah. That's actually, it's pretty neat, but yeah.
Okay, brilliant. That closes our talks. Thank you, Aditya.
Yeah, so thank you very much for the great talks today. And next we have our panel discussion to continue some of the thoughts that we already heard during the talks and discussions. We just need 2 minutes to convert the stage, and then we'll be right back. So maybe we can already ask our panelists also to join us on the stage.